Imagine standing on the surface of a world where the sun hangs in the sky like a giant white furnace. Its light is so intense that looking directly at it for even a moment can permanently damage your eyes. Its energy powers every forest on Earth, every ocean current, every breeze that moves across the continents, and every living thing that has ever existed. The surface of the sun burns at nearly 5,500 degrees Celsius. Deep inside its core, temperatures climb beyond 15 million degrees. Every second, it releases more energy than humanity could produce over millions of years. Now imagine drifting only a short distance away from that same sun. Not on Earth. Not protected by an atmosphere. But floating in the emptiness of space itself. Logic tells us that space should be unimaginably hot. After all, the sun is constantly pouring energy outward in every direction. There are no clouds to block its light, no weather to soften its warmth, and no night to offer relief. If anything, space should feel like standing inside a gigantic oven. Yet the reality could not be more different. Space is freezing. The average temperature of the universe is only about 2.7 degrees above absolute zero, or minus 270 degrees Celsius. That is colder than Antarctica has ever been. Colder than liquid nitrogen. Colder than almost anything we experience on Earth. How can both of these statements possibly be true? How can the hottest object in our solar system sit inside an environment that is almost unimaginably cold? At first, it sounds like a contradiction. It feels almost impossible, as though one of these facts must be wrong. But both are perfectly correct. In fact, understanding why space is so cold reveals one of the most surprising truths about our universe. It challenges something we have believed our entire lives without ever realizing it. We think of heat as something that naturally spreads everywhere. Put a heater inside a room, and eventually the whole room becomes warm. Build a campfire, and everyone sitting around it begins to feel its heat. Place a cup of coffee on the kitchen counter, and over time it cools until it reaches the same temperature as the surrounding air. Our everyday experiences have trained us to expect warmth to fill empty spaces. But space is not like your living room. Space is not like the air around a campfire. In many ways, space is the exact opposite of every environment your brain has ever experienced. The word space itself can be misleading. We imagine it as a giant container filled with darkness. In reality, it is almost completely empty. So empty that even the best vacuum chambers built by scientists on Earth contain far more particles than the emptiest regions between the stars. This emptiness changes everything. It changes how light travels. It changes how objects gain or lose heat. It even changes how astronauts experience sunlight. If you floated outside a spacecraft near Earth, something extraordinary would happen. The side of your suit facing the sun would become intensely hot, while the side facing away from the sun would become bitterly cold. Instead of existing inside one temperature, you would experience two completely different thermal environments at the same time. This sounds impossible because our brains are designed for Earth. Here, air constantly moves around us. Heat spreads quickly through the atmosphere. Temperatures blend together until everything feels relatively uniform. We rarely think about the invisible air surrounding us because it has always been there. Take it away, and the rules completely change. That is why one of the biggest challenges for spacecraft is not simply staying warm. Sometimes, the greatest challenge is getting rid of excess heat. Spacecraft are covered with reflective coatings, thermal blankets, radiators, and carefully engineered cooling systems. Without them, electronics could overheat even while floating inside one of the coldest environments imaginable. This raises another fascinating question. If space is so cold, why doesn't everything freeze solid immediately? Why doesn't sunlight instantly warm the vacuum around it? Why does a beam of sunlight travel through billions of kilometers of freezing emptiness without making that emptiness hot? The answers are hidden inside something we almost never stop to think about. What is heat? Not the feeling of warmth on your skin. Not the number displayed on a thermometer. But heat itself. What is it really? The answer turns out to be both simple and astonishing. Once you understand it, the mystery of cold space begins to disappear. And in its place emerges an even greater appreciation for how strange our universe truly is. Because the universe is not cold despite the sun. It is cold because of something far more fundamental. To understand why, we first need to rethink what temperature actually means. Most of us have spent our entire lives using words like hot and cold without ever asking what they actually mean. We know that boiling water is hot. Ice is cold. A summer afternoon feels warmer than a winter morning. The concepts seem so obvious that they hardly require explanation. Yet these familiar experiences hide an invisible world that behaves according to rules far different from our intuition. If you could shrink yourself until you were smaller than a single molecule, the universe would look nothing like the calm, solid world you know today. Everything around you would appear to be in constant motion. Molecules would race through space at incredible speeds, colliding billions upon billions of times every second. Atoms would vibrate continuously inside solids that seem perfectly still to our eyes. Even the chair beneath you, which feels completely motionless, is actually made of atoms that are constantly trembling. This endless microscopic motion is what temperature measures. When scientists say that something is hot, they are not describing a substance called heat. They are describing how much energy is contained in the motion of its particles. The faster those particles move, vibrate, and collide, the higher the temperature becomes. Imagine two rooms filled with thousands of tiny rubber balls bouncing in every direction. In one room, the balls drift slowly, gently tapping one another. In the other, they race around at incredible speed, striking everything with much greater force. Both rooms contain the same number of balls, but one contains far more energy. Temperature works in exactly the same way. Hot objects contain particles with greater average motion. Cold objects contain particles moving much more slowly. But this idea immediately introduces an even deeper mystery. What happens when there are almost no particles at all? This question is the key to understanding space. On Earth, heat moves constantly because we live inside a thick ocean of air. Every breath you take contains trillions upon trillions of molecules. Every room, every mountain, every city is surrounded by an invisible atmosphere packed with moving particles. When your skin feels warm, countless fast-moving air molecules are colliding with it. When your hands grow cold on a winter day, energy flows away from your skin into colder surrounding molecules. Without realizing it, we spend every second exchanging energy with the atmosphere. It is such a normal part of life that we rarely notice it. Now imagine removing almost every molecule around you. Not half. Not 99%. Almost all of them. The collisions stop. The invisible exchange of energy nearly disappears. Suddenly, one of the primary ways heat moves no longer exists. This is why the vacuum of space behaves so differently from anything on Earth. A common misunderstanding is that cold is something that exists by itself, almost like an invisible substance waiting to freeze anything it touches. But cold is not something that flows into an object. Heat flows out. Temperature falls because energy leaves, not because cold arrives. Think about placing a steaming cup of coffee on your kitchen table. Over time, it cools until it reaches room temperature. The room did not pour coldness into the coffee. Instead, energetic molecules inside the coffee transferred their energy to the cooler air surrounding it until both reached balance. Now imagine placing that same cup into the vacuum of space. There is almost no air waiting to absorb its heat. Almost no molecules to carry energy away through direct contact. The familiar cooling process that happens every morning in your kitchen would almost completely disappear. Yet the coffee would still cool. How? The answer is one of the greatest discoveries in physics. Heat has more than one way to travel. Some forms of heat require matter. One does not. It is this final method that allows the sun to warm Earth across nearly 150 million kilometers of empty space. It is also the reason sunlight can pass through the freezing vacuum without making the vacuum itself hot. At first glance, that seems impossible. But once we understand the three different ways heat moves through the universe, the contradiction begins to unravel. The emptiness of space is no longer a mystery. Instead, it becomes the very reason why our universe can contain both blazing stars and almost unimaginable cold at the same time. And that journey begins with the first of those three pathways, the one we experience every single day without ever noticing it. By now, we know that heat is simply energy in motion. We know that temperature measures how energetic tiny particles are, and we know that space contains almost none of those particles. But one enormous question still remains. If there is almost nothing in space, then how does the sun manage to warm the Earth from nearly 150 million kilometers away? Every second, sunlight leaves the surface of the sun and races across the solar system at the fastest speed the universe allows. About 8 minutes later, a tiny fraction of that light reaches our planet. It warms the oceans, melts snow, powers forests through photosynthesis, and makes life itself possible. Clearly, energy is crossing the emptiness. So why doesn't the emptiness become hot? The answer lies in understanding that heat has three different ways to travel. The first is conduction. This is the type of heat transfer you experience every time you touch something hot. Place a metal spoon inside a pot of boiling water, and after a few minutes the handle becomes too hot to hold. The heat didn't jump instantly from one end of the spoon to the other. Instead, energetic atoms inside the metal bumped into neighboring atoms, passing energy from one to the next, like a long line of people handing buckets of water down a chain. Conduction works wonderfully inside solids because their atoms sit close together. There is always another particle waiting to receive energy. The second method is convection. Unlike conduction, convection depends on moving fluids. Air and water are perfect examples. When air near a heater becomes warm, it expands and rises. Cooler air moves in to replace it, creating a continuous circulation that spreads heat throughout an entire room. The same process drives enormous weather systems across Earth and slowly stirs the oceans that regulate our planet's climate. Without convection, our weather would look completely different. Without convection, clouds would not form the same way. Without convection, hurricanes, thunderstorms, and even many ocean currents would never exist. But there is one important requirement for both conduction and convection. They need matter. Atoms. Molecules. Something physical to carry the energy. Space has almost none. Imagine trying to pass a message across a line of people. If the line stretches continuously from one person to the next, the message travels easily. But if every person is separated by hundreds of kilometers, the chain is broken. The message has nowhere to go. That is exactly what happens inside the vacuum of space. Conduction fails because there are no neighboring atoms. Convection fails because there is no air to circulate. If those were the only two ways heat could travel, Earth would be a frozen world, drifting through eternal darkness. Fortunately, nature has one more method. Radiation. Unlike conduction and convection, radiation does not need matter at all. Instead of relying on moving particles, radiation travels as electromagnetic waves. Visible light, infrared light, ultraviolet rays, radio waves, X-rays, and gamma rays are all members of the same enormous family. They differ only in their wavelength and energy. The sun constantly floods space with these invisible waves. They travel effortlessly through the vacuum, because they do not need molecules to carry them. They are the carriers themselves. This is why sunlight can cross millions, even billions of kilometers without slowing down. Empty space does not block it because there is almost nothing there to block. But this creates another subtle misunderstanding. When sunlight passes through empty space, it is carrying energy. Yet the space itself remains cold. To understand why, imagine standing beneath a spotlight inside a dark theater. The beam of light crosses the room, but the air inside the beam does not suddenly become hot. The energy continues traveling until it strikes something capable of absorbing it. The light itself is moving. The air is simply allowing it to pass. Space behaves in much the same way. Sunlight races through the vacuum carrying enormous amounts of energy, but unless that energy is absorbed by matter, almost nothing happens. When sunlight reaches Earth's surface, the story changes. Rocks absorb it. Oceans absorb it. Trees absorb it. Buildings absorb it. Even your skin absorbs part of that energy. As atoms inside those objects gain energy, they begin moving faster. Temperature rises. The sunlight did not heat the vacuum between the sun and Earth. It heated the matter that intercepted it. This is one of the greatest illusions created by living on Earth. We instinctively assume that sunlight heats the air. In reality, sunlight mostly heats the ground. The warm ground then heats the surrounding air through conduction and convection. Without the Earth's surface, the atmosphere would behave very differently. You can actually experience this effect yourself. Walk barefoot onto dark asphalt on a summer afternoon, and it may feel almost too hot to touch. Yet the air a meter above it is much cooler. The asphalt absorbed sunlight efficiently and converted it into heat. The surrounding air warmed only afterward. Space never gets that second step. There is no thick atmosphere waiting to distribute the energy. There is no ocean of molecules passing warmth from one place to another. There is only radiation traveling silently across unimaginable distances until it finally meets something real. This explains one of the strangest experiences astronauts describe. When they step outside their spacecraft, the side facing the sun receives intense radiation. Turn slightly, and another part of the suit may suddenly face deep space instead, losing energy toward one of the coldest environments imaginable. It is possible for different parts of the same spacesuit to experience dramatically different temperatures at exactly the same moment. Engineers spend years designing suits capable of balancing these extremes. Reflective outer layers bounce away excess sunlight. Insulating materials slow the movement of heat inside the suit. Cooling systems remove excess body heat before astronauts overheat. Ironically, overheating is often a greater concern than freezing. That surprises almost everyone. When people imagine space, they picture unbearable cold. Yet the greatest danger often comes from managing heat that has nowhere to escape except through radiation. The vacuum that prevents the sun from heating space also prevents warm objects from cooling quickly. The very emptiness that creates extreme cold also traps heat inside anything producing its own energy. It is one of the universe's most beautiful paradoxes. And it all begins with a simple fact. Empty space is almost perfectly transparent to sunlight. It lets the light pass. But it does not become warm. To truly appreciate how extraordinary that emptiness is, we need to understand just how empty space actually is. Because even the word vacuum barely begins to describe it. Most of us think we understand what empty means. Perhaps we imagine an abandoned room after all the furniture has been removed. Maybe we picture a desert stretching to the horizon with nobody in sight. Some imagine a cave deep underground where almost nothing disturbs the silence. But none of these places are truly empty. Even the cleanest room is filled with trillions upon trillions of air molecules. Every cubic centimeter around you contains an astonishing number of particles, all moving at hundreds of meters per second. Invisible collisions happen continuously. They are so numerous that your body never notices them individually. Now imagine climbing to the summit of Mount Everest. The air becomes much thinner. Every breath feels more difficult because there are fewer oxygen molecules entering your lungs. Yet even there, the atmosphere is still remarkably dense compared with space. Travel higher. 30 kilometers above Earth, weather balloons float through an atmosphere so thin that breathing without protection is impossible. Still, countless molecules surround every cubic centimeter. Continue upward until you reach the altitude where commercial satellites orbit. Here, the atmosphere has become so incredibly sparse that spacecraft can circle Earth for months before tiny traces of air gradually slow them down. Most people would call this a vacuum. Scientists would not. Because compared with deep space, even this region is crowded. As you leave Earth's atmosphere behind, the distances between particles become enormous. Molecules that once sat almost shoulder to shoulder are now separated by vast gaps. A single cubic centimeter may contain only a handful of atoms. Move farther still, beyond the orbit of the Moon. Beyond Mars. Beyond Jupiter. The solar system becomes quieter than anything the human mind naturally imagines. There are still particles here, mostly hydrogen atoms drifting through space, but they are astonishingly rare. A volume the size of a sugar cube may contain only a few lonely atoms wandering through darkness. Imagine standing alone in a city where every building has disappeared except one. Now imagine the nearest building is hundreds of kilometers away. That begins to resemble the emptiness between particles in deep space. Leave the solar system entirely and enter interstellar space, the immense region between stars inside our own galaxy. Here, distances become almost beyond imagination. Our nearest stellar neighbor lies over 4 light-years away, and between those stars stretches an ocean of near-perfect emptiness. There are still particles, magnetic fields, and faint clouds of gas, but compared with Earth they are almost nothing. Yet even this is not the emptiest place. Between galaxies, the universe becomes quieter still. Galaxies themselves are like islands, scattered across an unimaginably vast cosmic ocean. Between them lies intergalactic space, where matter becomes so scarce that enormous regions may contain only a few atoms within an entire cubic meter. Imagine a box 1 meter wide, 1 meter long, and 1 meter tall. On Earth, that box contains roughly 25 quintillion molecules. In intergalactic space, it may contain only a handful of atoms. That difference is almost impossible to comprehend. It is this astonishing emptiness that allows light to travel for billions of years without being scattered or absorbed. Photons born inside distant galaxies begin their journey long before Earth even existed. They cross immense cosmic voids almost untouched, finally reaching our telescopes after traveling longer than our species has been alive. The darkness between galaxies is not filled with freezing air. It is filled with almost nothing. And almost nothing cannot become hot in the way we instinctively imagine. Even the emptiest vacuum chambers built on Earth cannot compete. Scientists spend years removing every possible molecule from specialized chambers used for delicate experiments. Powerful pumps extract nearly all the air, creating conditions that seem impossibly empty by laboratory standards. Yet those chambers still contain millions or even billions more particles than many regions of deep space. Nature built a better vacuum than humanity ever could. This extraordinary emptiness affects more than temperature. It shapes the movement of galaxies. It allows radio signals from distant spacecraft to reach Earth. It lets starlight travel across billions of light years. It even influences how astronomers study the origins of the universe itself. But despite all this emptiness, space is not completely empty. There is something else filling every corner of the cosmos. Something that has been traveling through the universe since nearly the beginning of time. It is invisible to our eyes. It surrounds every galaxy. It passes through every planet. It flows through your body every second without you ever noticing. It is the oldest light in existence. And surprisingly, it gives the entire universe its faint temperature of just 2.7 degrees above absolute zero. To understand why even the emptiest parts of space are not at absolute zero, we must journey back nearly 14 billion years to the moment when the universe itself was born. If movies have taught us anything about space, it is probably this: if someone is exposed to the vacuum without a spacesuit, they freeze almost instantly. Within seconds, they become a solid block of ice, drifting silently through the darkness forever. It is one of the most common images in science fiction. It is also one of the most inaccurate. The truth is far stranger than fiction. In reality, freezing would not be your biggest problem. Lack of oxygen would. Imagine standing inside an airlock aboard a spacecraft. Behind you is safety. In front of you lies the vacuum of space. As the hatch slowly opens, every instinct tells you that unimaginable cold is waiting outside. But the vacuum itself is not an icy wind rushing toward you. There is no freezing breeze. There is no cold air at all. There is nothing. This is one of the hardest ideas for our brains to accept because every experience we have ever had with cold involved air. A winter morning feels cold because chilly air molecules constantly collide with your skin, carrying energy away. Step into icy water and you lose heat even faster because water transfers energy much more efficiently than air. Space has neither. Without air or water surrounding you, your body cannot lose heat through conduction or convection. Those two major pathways simply disappear. Instead, your body is left with only one way to release heat: radiation. And radiation is surprisingly slow. Your body continuously emits infrared radiation, even while you are sitting comfortably in your home. Every warm object does the same. The table beside you, your coffee mug, your phone, even the walls around you quietly glow in infrared light that your eyes cannot see. In space, this invisible glow becomes your primary cooling system. But unlike a gust of freezing wind, radiation removes energy gradually. This means your body would not instantly freeze. In fact, depending on whether sunlight was striking you, you might actually begin overheating before freezing became an issue. That sounds impossible. Yet spacecraft engineers spend enormous amounts of time solving exactly this problem. Inside the International Space Station, astronauts constantly generate heat simply by living. Their computers generate heat. Their life support systems generate heat. Their scientific equipment generates heat. Even the batteries quietly produce warmth while operating. On Earth, excess heat naturally escapes into the surrounding air. In orbit, there is no surrounding air. The station cannot simply open a window. Instead, enormous radiators extend from the structure like giant wings. These radiators do not cool the station by blowing away hot air. They cool it by slowly radiating infrared energy into deep space. Without them, temperatures inside the station would continue rising until electronics began to fail. Ironically, one of the coldest environments in the universe makes it difficult to get rid of heat. The same challenge exists inside every spacesuit. Many people imagine a spacesuit as an extremely thick winter coat. It is far more sophisticated than that. Beneath its outer layers, a modern spacesuit contains an intricate network of tiny tubes carrying cool water around the astronaut's body. This liquid cooling garment continuously absorbs excess body heat before transporting it to equipment that can slowly radiate the energy away into space. Without this cooling system, astronauts performing physically demanding work outside the station could overheat surprisingly quickly. Even though they are surrounded by the freezing vacuum of space. It is one of the universe's greatest ironies. The sun complicates this picture even further. When sunlight strikes an object in space, there is no atmosphere to weaken it. The full intensity of solar radiation arrives uninterrupted. Surfaces directly facing the sun can become extremely hot, while surfaces turned away lose heat toward the darkness of deep space. This creates extraordinary temperature differences. On the Moon, where there is almost no atmosphere, daytime temperatures can climb above 120 degrees Celsius. During the lunar night, temperatures can plunge below -170 degrees Celsius. The same ground experiences a difference of nearly 300 degrees. Places on Earth come anywhere close. This is why spacecraft are covered with reflective materials. Bright white coatings help reflect sunlight before too much energy is absorbed. Gold-coated visors protect astronauts from intense visible light and infrared radiation. Layers of insulation reduce the movement of heat through the spacecraft itself. Every material is carefully selected because every watt of heat matters. The challenge becomes even more fascinating when spacecraft travel far from the sun. Near Earth, engineers often worry about rejecting excess heat. Near Jupiter, sunlight is already 25 times weaker than it is here. Near Neptune, it is nearly 900 times weaker. Beyond Pluto, the sun no longer dominates the thermal environment in the way we naturally expect. It still shines brilliantly against the black sky, but its warmth has faded dramatically. Spacecraft traveling into these distant regions rely heavily on insulation and onboard power systems, simply to prevent instruments from becoming too cold. NASA's Voyager spacecraft have spent nearly half a century crossing this silent frontier. Even now, billions of kilometers from Earth, they continue transmitting faint radio signals back toward our planet. Tiny nuclear power sources provide electricity and heat, allowing delicate electronics to survive an environment colder than almost anything imaginable. Yet despite all these engineering marvels, one misconception remains remarkably persistent. People often ask what would happen if someone were suddenly exposed to the vacuum without protection. The answer is unpleasant, but not the one movies usually show. Within seconds, the lack of oxygen would cause unconsciousness. Pressure differences would affect the body. Moisture on the tongue and in the lungs could begin boiling because of the extremely low pressure, even though it was nowhere near boiling temperature in the everyday sense. But the body would not explode. It would not instantly freeze solid. Thermal changes would occur far more slowly than Hollywood suggests. Nature is almost always more subtle than fiction. The vacuum of space is not actively trying to freeze you. It is simply indifferent. It offers no warmth, no air, no protection, no convenient way for heat to move. It leaves every object alone with its own energy balance, slowly absorbing sunlight on one side while quietly radiating heat into the darkness on the other. And as we continue traveling farther from the sun, Even that sunlight gradually fades until another question begins to emerge. If the sun grows weaker and weaker with distance, just how cold can the universe actually become? The answer takes us to some of the coldest places known to science. When we think about cold, our minds usually travel to places on Earth. Perhaps we imagine Antarctica during the long polar winter, where temperatures can fall below -80 degrees Celsius. We picture endless fields of ice stretching toward the horizon beneath a pale blue sky. The air is so cold that each breath stings your lungs, and exposed skin freezes in only a matter of minutes. It feels like the coldest place imaginable. Yet by cosmic standards, Antarctica is surprisingly warm. Even the summit of Mount Everest, where climbers struggle to survive in bitter conditions, would feel almost comfortable compared with many regions beyond our planet. The journey toward true cosmic cold begins just beyond Earth. Our moon has no thick atmosphere to trap heat. During the 2-week-long lunar day, sunlight bakes the surface until temperatures soar above 120 degrees Celsius. But when night finally arrives, lasting another 2 weeks, the ground radiates its stored energy away into space. Nothing replaces it. Temperatures plunge below -170 degrees Celsius. This enormous swing is only possible because there is no atmosphere to spread heat from one place to another. Travel outward to Mars. The red planet receives less than half the sunlight Earth enjoys. Thin air provides little insulation. Winter nights near the poles can fall below -120 degrees Celsius, creating frozen landscapes unlike anything on our own world. Continue beyond Mars to Jupiter. Although Jupiter itself generates an internal heat left over from its formation, the sunlight reaching its cloud tops is only a small fraction of what reaches Earth. The giant planet glows softly in reflected sunlight, but the warmth of our star has weakened dramatically. Its icy moons tell an even more remarkable story. Europa hides a global ocean beneath kilometers of frozen ice. Ganymede, the largest moon in the solar system, remains locked beneath temperatures far below anything naturally found on Earth. Callisto preserves ancient scars from impacts billions of years old because so little changes in such extreme cold. As we travel farther, sunlight continues fading. Saturn receives only about 1% of the sunlight Earth does. At Uranus, daylight resembles the faint glow of late evening. By the time we reach Neptune, the sun appears little more than an intensely bright star. Its light is nearly 900 times weaker than it is on Earth. And still, the journey has only begun. Beyond Neptune lies the Kuiper Belt, home to countless icy worlds orbiting silently in the darkness. Pluto, once considered the 9th planet, spends much of its long year bathed in only the faintest sunlight. Surface temperatures hover around -230 degrees Celsius. Nitrogen freezes. Carbon monoxide freezes. Even gases that remain invisible on Earth become solid ice. Far beyond Pluto lies the mysterious Oort cloud, an enormous shell of icy bodies thought to surround the solar system. Some may orbit nearly a light year from the Sun. Out there, sunlight becomes almost meaningless. The warmth that once dominated our lives has dwindled into little more than a distant memory. Yet these places are still not the coldest known. One of the most extraordinary objects ever discovered is the Boomerang Nebula. Located thousands of light years away, this dying star has created conditions even colder than the faint background temperature of the universe itself. Expanding gas races outward so rapidly that it cools through a process known as adiabatic expansion. The result is astonishing. Temperatures inside the nebula have been measured at roughly 1 degree above absolute zero. Colder than the average temperature of space itself. It is one of the few known places where nature has managed to produce temperatures below the ancient glow left behind by the birth of the universe. That ancient glow is everywhere. Invisible microwave radiation fills every direction of the sky. It is unimaginably faint, yet sensitive instruments detect it no matter where they look. It is the oldest light in existence, traveling through space for nearly 14 billion years. Because of it, truly empty space is not exactly at absolute zero. Instead, almost the entire universe rests at approximately 2.7 Kelvin. That tiny amount of warmth has survived since the earliest moments of cosmic history. It surrounds every galaxy, every star, every planet, every human being. You are immersed in it right now, although your own body is far too warm to notice. The deeper we explore the universe, the more remarkable this becomes. Stars seem dominant because they are bright. Galaxies appear enormous because they contain hundreds of billions of stars. But almost all of the universe consists of darkness. Almost all of it is extraordinarily cold. Warmth is the exception. Cold is the rule. Every glowing star is a tiny island of energy surrounded by an ocean of near-perfect darkness extending for trillions upon trillions of kilometers. And yet, despite all this cold, the universe was not always this way. There was a time when every part of existence was unimaginably hot. Every atom, every photon, every tiny region of space. To understand why the universe eventually became so cold, we must travel back nearly 14 billion years to the greatest explosion, or perhaps more accurately, the greatest expansion, in cosmic history. Only then can we answer one final question. Why does empty space have a temperature of 2.7 Kelvin instead of absolute zero? The answer has been surrounding us since the beginning of time. For most of this journey, we have been asking why space is so cold. We have watched the warmth of the sun fade as we traveled farther from Earth. We explored frozen moons, distant dwarf planets, and lonely regions where only a handful of atoms drift through immense darkness. It would be easy to assume that the universe has always been this cold. But that could not be further from the truth. In fact, there was a time when the entire universe was so hot that not a single atom could exist. There were no stars, no planets, no galaxies, no people asking questions beneath a night sky. Only an expanding ocean of unimaginable energy. To understand how space became cold, we must travel backward through time, not millions of years, but billions. Every galaxy we observe through a telescope is not only distant in space, but distant in time. The farther we look, the younger the universe appears. Light itself becomes a kind of time machine, carrying ancient stories across unimaginable distances. If we could continue rewinding this cosmic history, galaxies would slowly move closer together. The vast empty spaces between them would shrink. Temperatures would rise. Matter would become increasingly dense. Eventually, we would reach a moment nearly 14 billion years ago when the observable universe occupied a volume far smaller than it does today. This event is commonly called the Big Bang. Despite the name, it was not an explosion into empty space. There was no gigantic fireball expanding into a waiting universe. Instead, space itself began expanding. Every region moved away from every other region, carrying galaxies along with the expanding fabric of the cosmos. Imagine dots drawn on the surface of a balloon. As the balloon inflates, each dot sees every other dot moving away. None of the dots sits at the center of the expansion because the surface itself is stretching. Our universe behaves in a similar way. During its earliest moments, temperatures were almost beyond comprehension. Matter as we know it could not exist because the energy was simply too great. Electrons could not remain attached to atomic nuclei. Even light struggled to travel freely because it constantly collided with charged particles filling the young universe. The entire cosmos resembled an enormous glowing fog. If you had somehow existed during that era, you would not have been able to see across even a short distance. Photons, the particles of light, were continually scattered in every direction, unable to travel very far before striking another particle. The universe was bright. Brilliantly bright. But completely opaque. As billions of years passed, or rather, as the universe expanded, the temperature slowly decreased. Expansion spread energy across ever larger volumes of space. Just as air cools while rising through Earth's atmosphere, the expanding universe gradually cooled as it grew larger. Then something extraordinary happened. Roughly 380,000 years after the Big Bang, the temperature finally fell enough for electrons to combine with atomic nuclei. For the first time, stable atoms formed throughout the universe. Suddenly, light no longer scattered endlessly from free electrons. The cosmic fog cleared. Photons that had been trapped since the beginning were finally free to travel. Many of those same photons are still traveling today. They have crossed the expanding universe for nearly 14 billion years without stopping. They have passed through forming galaxies, exploding stars, and countless empty voids. A tiny fraction eventually reached Earth, where radio telescopes detected them in every direction of the sky. This ancient light is known as the cosmic microwave background. At first glance, it seems impossible that light from the birth of the universe could still exist. Shouldn't it have disappeared long ago? The answer lies once again in expansion. As space stretches, the wavelengths of those ancient photons stretch with it. Originally, they carried tremendous energy. Today, after billions of years of cosmic expansion, their wavelengths have become so long that they belong to the microwave portion of the electromagnetic spectrum. They have cooled. Not because they lost energy to empty space, but because the universe itself expanded while they were traveling. Where brilliant visible light once filled the cosmos, faint microwave radiation now remains. Remarkably, this radiation gives empty space its average temperature of approximately 2.7 Kelvin. That means the vacuum is not completely cold. Every cubic centimeter of the observable universe is immersed in this faint afterglow from creation itself. Even here on Earth, these ancient photons pass silently through your home every second. They pass through mountains, through oceans, through your own body. You never notice them because they carry so little energy compared with the warmth surrounding us. Yet sensitive instruments detect them with astonishing precision. When astronomers map the cosmic microwave background, they are essentially photographing the oldest light that can ever be seen. It is not a picture of stars. Not a picture of galaxies. Not even a picture of planets. It is a portrait of the universe as an infant. Tiny differences in its temperature, only millionths of a degree, reveal subtle ripples that eventually grew into galaxies, galaxy clusters, and the enormous cosmic structures we observe today. Everything familiar began as incredibly small variations within this ancient sea of light. Without those tiny fluctuations, gravity would never have gathered matter into stars. Without stars, there would be no heavy elements. Without heavy elements, there would be no rocky planets. No oceans? No chemistry? No life? Every tree, every mountain, every heartbeat can ultimately trace its origins back to minute imperfections frozen into this ancient radiation. It is one of the most beautiful discoveries in modern science. The universe still remembers its beginning. Not through written records. Not through fossils. But through light itself. Every direction we look tells the same story. Everywhere we point our telescopes, the ancient glow surrounds us almost perfectly evenly, gently reminding us that the universe was once a single, unimaginably hot environment. Ironically, the reason space is so cold today is because it was once so incredibly hot. The expansion that created galaxies also diluted that original heat until only the faintest whisper remains. Yet even that whisper is enough to prevent empty space from reaching the coldest temperature theoretically possible. That raises another fascinating question. If space naturally settles around 2.7 Kelvin, could anything ever become even colder? Could absolute zero actually be reached? Or is there a fundamental limit built into the laws of physics themselves? The answer leads us into one of the strangest realms of modern science. Imagine removing every possible source of heat from an object. First, you cool it with ice. Then with liquid nitrogen. Then with liquid helium. You continue lowering its temperature until the atoms inside barely move at all. Surely, if you continue long enough, they must eventually stop completely. That final destination is known as absolute zero. It is the coldest temperature allowed by the laws of physics, exactly 0 Kelvin, or minus 273.15 degrees Celsius. At first, the concept seems straightforward. Temperature measures the motion of particles. Reduce that motion. Reduce the temperature. Stop all motion. Reach absolute zero. Simple. Except nature refuses to cooperate. Throughout the 20th century, physicists developed increasingly sophisticated ways to cool matter. They built powerful cryogenic laboratories capable of reaching temperatures only tiny fractions of a degree above absolute zero. They used lasers to slow atoms. Magnetic fields trapped particles in carefully controlled environments. Extraordinary engineering pushed the boundaries of what seemed possible. Each new experiment reached lower temperatures than the one before. Yet none reached zero. Again and again, the final fraction of a degree remained forever out of reach. Why? The answer lies deep within quantum mechanics. In our everyday experience, an object sitting perfectly still seems entirely reasonable. Place a book on a table, and it remains motionless until someone moves it. We naturally expect the microscopic world to behave the same way. But atoms obey different rules. Quantum mechanics tells us that particles can never possess perfectly defined position and perfectly defined motion at the same time. This remarkable principle, known as the uncertainty principle, introduces a kind of unavoidable restlessness into the universe. Even at temperatures unimaginably close to absolute zero, atoms retain a tiny amount of motion. Scientists call this zero-point energy. It is not caused by sunlight. Not by friction. Not by hidden sources of warmth. It exists simply because the quantum universe refuses to become completely still. In other words, perfect stillness may be physically impossible. This discovery completely changed humanity's understanding of cold. Absolute zero is not simply another temperature waiting to be reached. It represents a boundary, a limit built into reality itself. That does not mean physicists stopped trying. On the contrary, some of the most fascinating experiments in modern science occur only a billionth of a degree above absolute zero. At these astonishingly low temperatures, matter begins behaving in ways that seem almost magical. Certain materials lose all electrical resistance. This phenomenon, known as superconductivity, allows electric current to flow without wasting energy as heat. Powerful superconducting magnets make technologies like MRI scanners and particle accelerators possible. Other materials become superfluids. Imagine a liquid that flows forever without friction. A liquid capable of climbing the walls of its own container. A liquid that behaves less like ordinary water and more like a single gigantic quantum object. Such substances exist. Not because the laws of physics break down, but because we are finally seeing those laws in their purest form. Cooling matter also reveals one of the strangest states ever discovered, the Bose-Einstein condensate. Normally, atoms behave as individual particles. Near absolute zero, something remarkable happens. Large numbers of atoms begin acting together as though they were one enormous quantum wave instead of countless separate particles. The distinction between individual atoms starts to disappear. Matter itself acquires properties that simply do not exist at everyday temperatures. These discoveries remind us that temperature is not merely a measure of comfort. It changes the very nature of reality. A universe at room temperature behaves one way. A universe only a tiny fraction above absolute zero behaves in ways that challenge even the most experienced physicists. Fortunately for us, Earth exists comfortably between these extremes. Our planet is warm enough for liquid water. Warm enough for chemistry. Warm enough for life. If the entire universe existed near absolute zero, atoms could still exist, but the dynamic processes that make biology possible would become unimaginably different. In many ways, life occupies a narrow thermal window within an overwhelmingly cold cosmos. Outside that window lies the silent universe we have been exploring. But there is an even greater story waiting ahead. The ancient heat from the Big Bang continues fading. Stars slowly consume their nuclear fuel. Galaxies gradually evolve. Over trillions upon trillions of years, the universe itself will continue cooling. The warmth that remains today is only temporary. One day, even the brightest galaxies may disappear into darkness. The cold we experience now is not the end of the story. It is only the beginning of the universe's long journey toward its final fate. Everything that feels permanent eventually changes. Mountains slowly wear away beneath wind and rain. Oceans reshape coastlines one wave at a time. Even the stars, which appear so constant in our night sky, are living on borrowed time. They are born, they shine, and one day they die. The universe itself is no exception. Although space already feels unimaginably cold, it is actually warmer today than it will be in the distant future. The stars surrounding us continue producing enormous amounts of energy every second. Galaxies still glow with the light of hundreds of billions of suns. Black holes consume matter, releasing tremendous energy as gas spirals inward. Across the cosmos, countless sources of heat continue to illuminate the darkness. But none of them will last forever. Imagine standing beside a campfire late at night. At first, the flames burn brightly, filling the air with warmth and light. As the wood is consumed, the fire gradually weakens. The flames become smaller. The glowing embers fade from orange to deep red. Eventually, only a few faint sparks remain before darkness quietly returns. The universe is following a similar story. Only on a timescale so enormous that it almost defies comprehension. The stars shining above Earth today are powered by nuclear fusion. Deep inside their cores, hydrogen atoms combine to form helium, releasing astonishing amounts of energy in the process. That energy slowly works its way outward before escaping into space as sunlight. Every sunrise on Earth is powered by reactions that began deep inside the Sun hundreds of thousands of years ago. Yet hydrogen is not infinite. Every second, our Sun converts roughly 600 million tons of hydrogen into helium. Although that sounds alarming, the Sun contains such an enormous supply of fuel that it can continue shining for about another 5 billion years. Eventually, however, even that immense reserve will be exhausted. The Sun will swell into a red giant, transforming the inner solar system forever. Mercury will disappear. Venus almost certainly will as well. Earth's future remains uncertain, but even if our planet survives physically, its oceans will have vanished long before. The Sun will not explode in a dramatic supernova. Instead, it will quietly shed its outer layers into space, creating a beautiful glowing shell known as a planetary nebula. At its center, the remaining core will become a white dwarf, a dense stellar ember slowly cooling across billions of years. That lonely white dwarf will continue fading. Not because something is making it colder, but because it will simply radiate away the heat it already possesses. Across the Milky Way, similar stories will unfold. Massive stars live fast and die young, ending their lives in spectacular supernova explosions. Smaller stars burn fuel more slowly, surviving for hundreds of billions or even trillions of years. Tiny red dwarfs, the most common stars in the universe, may continue shining long after every sun-like star has disappeared. Eventually, though, even they must fade. One by one. Galaxy by galaxy. The lights slowly go out. Astronomers sometimes refer to this unimaginably distant era as the degenerate era. Ordinary stars have disappeared. White dwarfs slowly cool. Neutron stars become darker. Black holes dominate much of what remains. The universe becomes quieter than it has ever been before. This gradual cooling is driven by one of the deepest principles in all of physics. Entropy. Entropy is often described as the tendency for energy to spread out. Imagine pouring a drop of ink into a glass of water. At first, the ink remains concentrated in one location. Given enough time, it spreads throughout the entire glass until it becomes evenly distributed. The reverse process never happens naturally. The ink never spontaneously gathers itself back into a single drop. Heat behaves in much the same way. Energy naturally flows from hotter regions toward colder ones until temperatures become more uniform. A hot cup of tea cools to room temperature. A glowing iron rod eventually becomes cold. Every process gradually moves toward greater balance. The universe follows this same rule. Stars represent enormous concentrations of energy. Over trillions upon trillions of years, that energy disperses into the vast emptiness of space. The result is sometimes called the heat death of the universe. The name sounds dramatic, but it does not mean the universe freezes overnight. It describes a future in which useful energy has become so evenly distributed that almost nothing interesting can happen anymore. No new stars ignite. No great sources of warmth remain. The cosmos settles into an almost perfectly uniform darkness. Imagine an ocean without waves. A forest without wind. A sky without sunrise. Everything still exists. Nothing dramatic happens. The universe simply becomes quieter. Slower? Colder. This possibility raises profound philosophical questions. Will anything remain to witness such a future? Will life survive long enough to see the last stars disappear? Could advanced civilizations somehow adapt to an ever-cooling universe? Scientists have imagined remarkable possibilities. Some suggest civilizations might migrate toward long-lived red dwarf stars. Others imagine harnessing the energy of black holes. Some speculate about slowing subjective time itself, stretching finite energy across unimaginable spans. Whether any of these ideas could ever become reality remains unknown. But one conclusion appears unavoidable. The universe we know today is temporary. We happen to live during one of the brightest chapters in cosmic history. The night sky still sparkles with countless stars. Galaxies still collide. New solar systems continue forming. Planets continue cooling. Life continues emerging. Billions of years from now, observers living elsewhere in the cosmos may look up into skies far darker than ours, wondering whether the universe had always been so empty. In a sense, we are living during springtime. The universe is still full of light. Yet eventually, even spring gives way to winter. And when that unimaginable winter finally arrives, only scattered remnants of today's brilliant universe may remain. But before we leave the present behind, there is one question nearly everyone has wondered at some point in their lives. What would actually happen if you found yourself alone in the vacuum of space? Would you freeze? Would you boil? Or would something entirely different occur? Few scenes appear more often in science fiction than this one. A spacecraft suffers catastrophic damage. An airlock suddenly opens. Someone is thrown into open space. Within moments, their body freezes solid, covered in glittering ice before drifting silently into the darkness. It is a memorable image. But reality tells a different story. Imagine, for just a moment, that you are wearing no protective suit and suddenly find yourself exposed to the vacuum of space. The first thing you would notice is not freezing. It is silence. Complete silence. Sound cannot travel through empty space because there are no air molecules carrying vibrations from one place to another. Explosions would appear almost graceful, expanding silently against the darkness. Even if another spacecraft were only a short distance away, you would hear nothing at all. Next comes the absence of air. Your lungs contain only the oxygen already inside them. Without a fresh supply, your blood rapidly begins losing oxygen. Within roughly 10 to 15 seconds, the brain no longer receives enough to maintain consciousness. You lose awareness? This happens long before freezing could become significant. One important detail often misunderstood is breathing. If someone knew they were about to be exposed to vacuum, holding their breath would actually make the situation far more dangerous. As external pressure disappears, trapped air inside the lungs expands. Attempting to keep that expanding air inside can seriously damage delicate lung tissue. Instead, the safest response, counterintuitive though it sounds, would be to exhale. Pressure changes also produce another surprising effect. At sea level, water boils at 100 degrees Celsius. But boiling does not depend only on temperature. It also depends on pressure. Reduce pressure enough, and liquids begin boiling at much lower temperatures. In the vacuum of space, moisture on the surface of the tongue, inside the mouth, and within exposed tissues could begin vaporizing despite being nowhere near what we normally consider hot. This sounds terrifying, yet it does not mean your entire body suddenly boils away. Your skin provides remarkable protection. The human body is tougher than many people realize. Contrary to popular myths, your body would not explode. Your eyes would not burst. Your blood would not instantly boil inside your veins, because the circulatory system remains pressurized internally. However, gases dissolved within body fluids may gradually form bubbles, causing swelling known as ebullism. Soft tissues could expand noticeably, though not catastrophically. Experiments and accidental exposures have taught scientists valuable lessons about how the body responds. During the early years of space exploration, engineers carefully studied these possibilities while designing pressure suits capable of protecting astronauts. In one famous incident during a vacuum chamber test, a technician experienced accidental exposure after a suit malfunctioned. He later reported losing consciousness after roughly 14 seconds. Upon recovery, one of his final memories before blacking out was feeling saliva on his tongue begin to boil. Remarkably, he survived. The human body proved far more resilient than many had expected. Thermal effects, meanwhile, develop much more slowly than Hollywood suggests. Remember what we learned earlier. There is no freezing wind in space. No icy air stripping warmth from your skin. Without conduction and convection, your body can lose heat only through radiation. Radiation works continuously, but gradually. If sunlight happened to strike you directly, parts of your body might actually absorb energy faster than they could radiate it away. One side could become warmer while the opposite side steadily cooled toward deep space. Your experience would depend heavily on orientation, sunlight, and surrounding conditions. Another invisible danger quietly surrounds you. Radiation. Earth's atmosphere shields us from much of the sun's harmful ultraviolet radiation, while our planet's magnetic field helps deflect many energetic charged particles arriving from space. Remove those protections, and the environment becomes much harsher. For short exposures, lack of oxygen remains the immediate threat. For longer exposures, radiation becomes increasingly significant. Micrometeoroids add yet another hazard. Tiny grains of dust travel through the solar system at tens of kilometers per second. Most are incredibly small, but at such extraordinary speeds, even a particle smaller than a grain of sand carries surprising energy. Space is often described as empty. It is. But empty does not mean harmless. Perhaps the greatest lesson from this thought experiment is how profoundly Earth protects us every moment of our lives. Our atmosphere supplies breathable oxygen. It distributes heat evenly around the globe. It burns up most incoming meteoroids before they reach the ground. It filters dangerous radiation. It maintains pressure that allows liquid water, and life itself, to exist comfortably on the surface. We rarely notice these protections because they have always been there. Only by imagining their complete absence do we begin to appreciate how extraordinary our planet truly is. The vacuum of space is not an evil force waiting to destroy anything that enters it. It simply follows the laws of physics with perfect indifference. It neither welcomes nor rejects life. It offers no warmth, no air, no protection, only silence. And perhaps that silence is the greatest reminder of all, that the tiny blue world we call home is far more remarkable than it first appears. As children, many of us draw the universe in much the same way. A bright sun. A few colorful planets. Perhaps a field of stars scattered across a black sky. It feels natural to imagine that the universe is mostly filled with glowing objects, and that darkness simply exists in the spaces between them. But the truth is almost the opposite. The universe is not mostly stars. It is not mostly planets. It is not mostly galaxies. The overwhelming majority of the cosmos is empty, dark, and astonishingly cold. Everything warm that has ever existed occupies only the tiniest fraction of all space. Think about our own solar system. The sun dominates every picture we have ever seen. It is so large that it contains more than 99.8% of all the mass in the solar system. It appears to fill the center of our cosmic neighborhood, making everything else seem almost insignificant. Yet if we step back far enough, something remarkable becomes obvious. The sun itself is incredibly small compared with the empty volume surrounding it. If the solar system were represented by a giant sphere extending to the distant Oort cloud, nearly all of that enormous volume would contain almost nothing. The planets occupy only tiny specks. The asteroids are separated by vast distances. Comets spend most of their lives drifting through immense darkness. Even the sun itself becomes a small glowing point inside an almost incomprehensible ocean of emptiness. Now expand your view. The Milky Way contains hundreds of billions of stars. That sounds crowded. It is not. The average distance between neighboring stars is measured in trillions of kilometers. If our sun were reduced to the size of a grain of sand, the nearest star would still be several hundred kilometers away. Everything in between would be almost perfectly empty. The galaxy is not a dense forest. It is more like a handful of fireflies scattered across an entire continent. Travel farther still. The observable universe contains trillions of galaxies, each separated by millions of light-years of nearly empty space. Massive galaxy clusters appear impressive in telescope images because cameras expose them for hours, gathering light that has traveled for billions of years. But if you could stand there with your own eyes, you would find yourself surrounded mostly by darkness. The universe is built from islands. Between those islands stretches an ocean larger than imagination itself. This changes the way we should think about heat. Our daily experience tells us that warmth is normal. Every morning, sunlight reaches Earth. We cook our food with fire. Our homes are heated in winter. Our own bodies continuously generate warmth simply by being alive. Everything around us reinforces the idea that heat is the natural condition of the universe. In reality, Earth is an extraordinary exception. The warmth surrounding us exists only because we orbit an active star at just the right distance. We live inside a remarkably thin shell of atmosphere that traps enough heat for liquid water to exist without allowing temperatures to become unbearably high. Move a little closer to the sun, and oceans disappear. Move a little farther away, and they freeze. The region where liquid water can persist is astonishingly narrow compared with the enormous scale of the solar system. Our planet exists inside a tiny thermal oasis. Stars create similar islands throughout the galaxy. Around each star, there may exist a small region where temperatures allow chemistry to become wonderfully complex. Molecules combine into new forms. Planets develop atmospheres. Oceans appear. Perhaps, under the right circumstances, life begins asking questions about the universe that created it. Outside those rare islands lies the overwhelming reality. Cold. Darkness. Silence. The remarkable thing is not that space is cold. The remarkable thing is that any place is warm at all. Every glowing star fights a constant battle against the universe's natural tendency toward balance. Fusion inside stellar cores continuously pushes back against gravity while releasing vast amounts of energy into surrounding space. Eventually, gravity wins. Fuel runs out. Stars fade. The islands slowly disappear. Yet for a brief cosmic moment, those islands transform the universe. Inside stars, hydrogen becomes helium. Later, helium becomes carbon. Still later, oxygen, silicon, and iron are created within the most massive stellar furnaces. During violent supernova explosions, even heavier elements are forged: gold, uranium, iodine, calcium, and dozens more. Everything in your body heavier than hydrogen originated inside ancient stars. The calcium in your bones. The iron in your blood. The oxygen you breathe. The carbon forming every living cell. All were manufactured inside places that were once unimaginably hot. Long before Earth existed. Long before the sun was born. When those ancient stars died, they scattered their elements across space. Gravity later gathered those materials into new stars, new planets, and eventually into us. In a beautiful sense, every warm star that ever existed contributed something to the existence of life. We are not separate from the universe. We are one of its consequences. That realization transforms our original question. We began by asking why space is so cold if the sun is so hot. Perhaps the better question is this: why does the universe contain stars at all? Why does gravity occasionally gather enough matter together to ignite these magnificent furnaces that interrupt the endless cold? Without them, the universe would remain almost perfectly dark. Almost perfectly frozen. Almost perfectly silent. Stars are not the rule. They are the miracle. And every living world exists because of them. As our journey comes to an end, there is one final perspective that brings everything together. A perspective that begins not with the sun, not with Earth, but with you. Tonight, after this journey ends, you may find yourself looking differently at the night sky. Perhaps you will step outside for a moment. Perhaps you will simply look through a window. The stars will appear exactly as they always have. Tiny points of light scattered across a vast darkness. Nothing about the sky itself will have changed. Only your understanding of it. Every one of those distant stars is surrounded by an ocean of freezing emptiness extending for trillions upon trillions of kilometers. Their light has crossed enormous cosmic deserts where almost nothing exists. It traveled through silence so complete that no human experience can truly compare to it. And after crossing all of that darkness, a few tiny photons finally reach your eyes. That simple act of seeing the stars is more extraordinary than it first appears. Those photons began their journey years, centuries, or even thousands of years ago. Some left their stars before the first pyramids were built. Others departed long before the Roman Empire existed. The light arriving tonight is ancient, carrying stories written across unimaginable distances. Yet all of those stories have something in common. They remind us that warmth is precious. Our entire civilization exists on a remarkably small island of energy. Every meal we eat ultimately traces its energy back to sunlight captured by plants. Every forest grows because a nearby star continuously shines. Every wind blowing across the oceans is powered by uneven heating from the sun. Every drop of rain, every cloud, every season, every ecosystem exists because our planet receives just enough energy to remain alive. If the sun suddenly disappeared, Earth would not immediately freeze solid. The atmosphere and oceans would retain heat for a while. But over weeks, months, and years, temperatures would steadily fall. Plants would die as sunlight vanished. Oceans would gradually freeze from the top down. Eventually, only geothermal warmth deep beneath Earth's crust would remain. Our comfortable world would slowly become another frozen object drifting through space. This thought reminds us how delicate our existence truly is. The distance between survival and impossibility is measured not in millions of kilometers, but in a careful balance of energy maintained every single second. The universe does not guarantee warmth. It merely allows it to exist in rare places for limited periods of time. And somehow, against overwhelming odds, one of those places became our home. There is another lesson hidden inside this story. When we first asked why space is so cold, it seemed like the universe was doing something strange. Now we realize the opposite. Cold is not mysterious. Cold is the default. Heat is what requires explanation. Heat appears only where energy is concentrated. Inside stars. Inside planets. Inside living creatures. Inside every human heart quietly converting chemical energy into warmth with every beat. You carry a tiny piece of the universe's energy history within you. The atoms making up your body were forged inside stars. The energy powering your thoughts came from sunlight that nourished plants, directly or indirectly, over countless generations. Even the warmth of your own skin is a reminder that you are part of an unbroken chain stretching back nearly 14 billion years to the birth of the cosmos. Perhaps that is the most beautiful answer to our original question. The sun does not make space hot because space is almost empty. There is simply too little matter to absorb its energy. Light crosses the vacuum effortlessly, waiting until it finds something real, something capable of turning that radiant energy into warmth. Earth is one of those rare places. So are you. For a brief moment in cosmic history, the atoms born inside ancient stars have assembled themselves into beings capable of wondering why the universe is the way it is. Out of endless darkness came light. Out of cold came warmth. Out of simple atoms came curiosity. That may be the rarest phenomenon of all. The universe is nearly 14 billion years old. It spans hundreds of billions of light years. It contains trillions of galaxies and more stars than there are grains of sand on every beach on Earth. Yet almost all of it is silent. Almost all of it is cold. Almost all of it is empty. Against that immense backdrop, our world is a tiny blue oasis orbiting an ordinary star in the outskirts of an ordinary galaxy. And somehow, that has been enough. Enough for oceans to form. Enough for life to appear. Enough for minds to evolve. Enough for one species to build telescopes, leave its planet, measure the temperature of empty space, and ask one beautifully simple question. Why is space so cold when the sun is so hot? Now we know the answer. Not because the universe is trying to keep itself cold. Not because the sun is too weak. But because emptiness cannot hold warmth. The stars are not heating space. They are illuminating it. And in that vast ocean of darkness, every star, every planet, every living world, and every conscious mind becomes something infinitely more precious than we ever imagined. As you close your eyes tonight, remember that beyond the warmth of our atmosphere stretches an almost endless sea of silence only a few degrees above absolute zero. Yet scattered throughout that immense darkness are tiny islands of light, each pushing back against the cold for a little while. We happen to live on one of those islands, during one of the brightest moments the universe will ever know. Perhaps that is what makes our existence so extraordinary. Not that the universe is warm. But that, against all odds, one small corner of it became warm enough for us to wonder why.